Okay, let's continue on chapter 2, polynomials and rational functions. We're going to get started on section 2.1. And we're going to take a look at quadratic functions and then models. So quadratic function typically we write as ax squared plus bx, that is c. A cannot be 0. Okay. So we're going to learn how to analyze the graph of the quadratic functions. And we're going to write the quadratic functions in standard form and use a result to sketch the graph of the function. We're also going to learn how to find the minimum, maximum values of quadratic functions in real-life applications. First of all, let's take a look at graph of quadratic functions. So it's either opens upward. There's two major categories. We call this graph parabola. This one opens upward. And then we also have a parabola opens downward. So we already learned the linear function. So linear function is ax plus b, or mx plus b. And we also have learned a constant function in chapter 1 and a squaring function from chapter 1. And we know what the graph look like. And these functions are examples of polynomial functions. And we call this degree 1. Linear function is degree 1. Or first degree. Polynomial function, because the leading power here is 1. So the leading power determines the degree of the polynomial function. And this one is what we call degree 0. Because there's no x to a 0 power here. So we can always add x to a 0 power becomes 1. So the power is degrees 0 degree. And the third one is the second degree, or degree 2. Because the leading power is 2. Okay. So leading power determines the degree of the polynomial function. Leading power determines the degree of the polynomial function. Okay, so let's take a look at general form of polynomial, any polynomial function. Let them be the non-negative integers, an minus 1, all the way to a0 be real numbers with an cannot be 0 here, so the leading term here is an xn. So we know that from the leading term, this is degree n degree polynomial function. And also, given that an cannot be 0, if an is 0, then it's not a nth degree polynomial function. So this polynomial function of x with a degree n. So it's polynomial function classified by degree, and typically it's determined by the leading power. So the constant function has a leading power 0, and then linear function has leading power 1. Okay. In this section, we will study second degree polynomial function. We call these quadratic functions. So now let's take a look at some example of quadratic function. Again, I'm gonna give you the leading term here. First leading term is x squared. Second leading term is 2x squared if you expand it. And the third leading term is a quarter x squared. And fourth one is negative 3x squared. And last one is x squared. And if you look at all of this, they all have a leading power of 2. That's why all of this is a second degree polynomial function. And definition of quadratic function, a, b, and c be real numbers. A cannot be 0 again. If a is 0, then we have a linear function, not a quadratic function. F of x equals ax squared plus bx. Adding c is called a quadratic function. The graph of quadratic function is a special type of U-shaped curve called a parabola. So either opens upward, opens downward. And if you look at the application in real life, if you play baseball or basketball, the way how the ball travels, actually, if you pay close attention, it's a parabola shape. So this is a real life application of the parabola. Now all parabola has a symmetry line with respect to, we call this axis of symmetry, or you can also call the axis of parabola. The point where the x-axis intercept the parabola is vertex of the parabola. Okay. Axis of symmetry intercept the parabola is the vertex of the parabola. And typically, if a is greater than 0, meaning parabola opens upward, then we have a vertex here. Vertex is equivalent to minimum here. You can also call this the lowest point. That's why it's the minimum. And also, you can look at this as a valley. The bottom of the valley. Okay, and that's why it's the lowest point. It's the minimum. And if the parabola opens downward, that means leading coefficient a is less than 0. So it opens downward. Then the vertex is the same thing as the highest point. You can also say that maximum. Vertex is equivalent to maximum. And then if you look at this, look like a heel here. So on top of the heel, you get a highest point. Yeah. And that's where the maximum value occurs. And these two are very crucial in the real life, applications. In different industry, they use this to model a certain scenario, and also use minimum maximum to determine to make decision. Okay, so when the leading coefficient is positive, that means when a is greater than 0, that means parabola opens upward. Opens upward. Then given the implication is vertex equal to minimum. Okay, and then when a is less than 0, meaning leading coefficient is less than 0, then parabola opens downward. Then the vertex is the same thing as maximum. Okay. And the simplest type of quadratic function is f of x equals ax squared. Again, a cannot be 0. Okay. So we just do a vertical distortion to manipulate the graph in order to get all these transformation function from the parent function. So the parent function we talk about should be y equal to x squared. Okay. So now again we're still talking about f of x equal to ax squared. And if a is greater than 0, that means the vertex is the minimum value, and we know that the minimum value is the origin, and the vertex is the minimum. Vertex. Okay. And if a is less than 0, like this, it opens downward, then the vertex is equal to maximum. The maximum occurs at 0, 0. And now when sketching a graph of f of x equal to ax squared, it's helpful to use a graph of y equal to x squared as a reference. For example, we just apply some transformation to come up with the graph of the transformation functions. And for example, if you want to sketch each of the quadratic function below and then compare with the graph y equal to x squared, we look at f of x. So going from y equal to x squared to f of x, we need to do a vertical. This is vertical shrink. Okay. By a factor of 1/3. That means the graph becomes wider. So we end up with a wider graph. So the smaller the coefficient, the wider graph we get. Vertical shrink meaning horizontal stretch. That actually happen at the same time. The second one, compared with y equal to x squared, we have a leading coefficient of 2. That means we have a vertical stretch. By a factor of 2. Yep. That means the graph becomes narrower. Narrower indicates we have vertical shrink, horizontal shrink, and equivalent to vertical stretch. So when absolute value of we look at the model f of x equal ax squared, when absolute value of a is small, the parabola opens wider than when the absolute value of a is large. And we know that graph of this is first one adding or subtracting c, this is horizontal shift. And we learned it from chapter 1. And adding or subtracting c for the entire function, this is what we call a vertical shift. And then if x becomes negative x, this is what we call refraction by the y-axis. The last one, when the y value becomes opposite, and this is a refraction about the x-axis. Okay, so we just, if any of this transformation happens, we just apply the transformation. Then we can go from the parent function to our transformation function in the graph. For example, let's say we have a parent function y equal to x squared. The first function is f of x. So let's describe the transformation here. We have the graph. So step 1, here you will do a reflection about the x-axis. So get this graph first. So from this gray graph, we do a reflection about the x-axis. Then that's step number 1 about the x-axis. Then after that, we just shift the graph 1 unit upward. So move up 1 unit, the graph move up 1 unit. Okay, then we come up with a targeted graph, which is f of x. And now second function here, second graph, we look at it. This is the parent function. First of all, we're gonna shift the parent function 2 units to the left. Right, so we come up with this. And after we do that, then first of all, let's write it down. Move 2 units to the left. To the left. Then second step, you're gonna move down 3 units. So each one of these move down 3 units, and we'll stop right here. Then second move is move down 3 units. So it's 2-step transformation from the parent function. We end up with the g of x. So making connection using the knowledge we already learned to solve this newly acquired knowledge. So let's take a look at standard form of the quadratic function. So the standard form usually is written as a times x minus h parentheses square plus 8k, and then here the vertex it's given vertex is going to be hk. Okay. And the way how we get the x coordinate, we just setting x minus h equals 0, then you get a. Also, we find the axis of symmetry. So here x equal h is the axis of symmetry. Also, that's x coordinate of the x coordinate of the vertex. Okay. All right. So we have a quadratic function of x equal to a times parentheses x minus h plus parentheses square plus k. A cannot be 0, and this is what we call standard form. And when a is greater than 0, then parabola opens upward. We have a parabola like this. Then vertex is same thing as minimum. A less than 0, when parabola opens downward, and the vertex is the maximum. And again, in terms of coordinate, vertex, the coordinate for vertex is hk. And an axis of symmetry is x equal h. Those two are the most important element when we're talking about quadratic functions. And now, to graph a parabola, it's helpful to begin by writing quadratic function in standard form. And in that, typically we need to use a process of completing a square method. So if you get a parabola in the general form, then you're going to turn it into a standard form, and then we need a completing a square. And now let's take a look at how we do that. So let's say we have f of x equal to 2x squared plus ax plus 7. So first of all, you write down this equation: 2x squared plus ax adding 7. So in order to complete the square, you're going to keep the first two terms. Okay, and then since they have common factor, so you're going to factor by GCF by 2 and get x squared plus 4x. Alright, adding 7. So we just split into two elements. One of them are two terms needed to complete the square to create a perfect square. The other term is constant. You leave it outside of the parentheses. Now the next step is come up with a constant. So you're taking the middle number 4, okay, and divide by 2, we squared it, we get a constant we're looking for. So it turned out to be 2 squared, and 2 squared is 4. Okay. So the constant we're looking for to create a perfect square is 4. So now we add 4 here. Since we add 4, we get to subtract 4 to keep the balance. Okay. So this is a very important step. You cannot just add 4 to a function without compensating that, or without eliminating the effect of that. So here the way how we taking care of that is subtracting 4 at the same time. So now the first 3 terms is what we call a perfect square. We're going to keep those 3 terms. So they're going to distribute 2 to -4 and then move it outside. So we get 2. Now inside parentheses we get perfect square 4x plus 4. Okay. 2 times -4 is -8. So it goes outside. Now you combine those 2 constants, and then inside of the parentheses perfect square 2x plus 2 square. Okay. Now we complete the square. And at -8 plus 7, that's -1. Okay, so now we turn this into a perfect square, and then we will be able to get a vertex. First of all, that's the way how we nail down a vertex is by setting x plus 2. Okay, actually, let's do the axis of symmetry first, because that's easier. Okay, so let's find the axis of symmetry first. So once we complete the square, the axis of symmetry you're just setting whatever inside parentheses equal to 0, then we get axis of symmetry x equal -2. That's what we call the axis of symmetry. Okay, and then once we find x coordinate, axis of symmetry, actually we also find part of the vertex. So vertex here, x coordinate must be -2, y coordinate is -1. Okay. And again, those 2 are important, most important elements in Parabola. And that's how we get it. By completing the square first. And once you do that, you'll be able to find out axis of symmetry and then vertex. Okay, so now we have this parabola or quadratic function in the standard form. Now with the vertex, we already figured out that. And now if you look at the graph here, the transformation here from y equal to 2x squared is shifting to the left 2 unit. Look at this graph first. And shift down to 1 unit. So 2-step transformation from the parent function y equal to 2x squared, move to the left 2 unit. And then after that, move downward 1 unit. Move down 1 unit. Then we get our function f of x after we apply this 2-step transformation. And to find the x-intercept of the graph of f of x equal ax squared plus bx at a c, we basically just setting f of x equal to 0. X-intercept is setting f of x equal to 0, setting y equal to 0, and solve for this equation. And most of the time we could factor this, right? And then solve for x. If we cannot factor, does not factor, if ax squared plus bx at c does not factor, then we can use the quadratic formula to find the x-intercept. And the quadratic formula is -b plus minus radical b squared minus 4ac over 2a. Okay, so just use the formula to come up with the x-intercept. And sometimes the problem may not have the x-intercept when this, even using the quadratic formula, we have no solutions, right? It's possible. then the parabola has no intercept. Okay. Now let's look at how to find minimum value of maximum values. Okay. So in order to find minimum and maximum values, we still need to use the completeness square method to go from the standard form. Let's say f of x equal ax plus bx adding c. We're going to turn this into the standard form. So again, we're going to keep the first two terms and we factor out the a, put it into the parentheses, so we get x squared plus b over ax. Okay. Now as usual, we're going to add a constant here, and the way how we get it, the constant is by dividing the middle coefficient, so b over a by 2, right? Divide by 2 times means multiply by half, and we squared it. So multiply across, we get b over 2a, and we squared it. Now square the top, we get b squared. Square the bottom, we get 2 squares 4a squared. So the constant we're looking for is b squared over 4a squared. So you're gonna add that b squared over 4a squared. And you're gonna subtract the same thing, minus b squared over 4a squared. Okay. Now the first three terms are what we call perfect square, and we're going to distribute the last term will be outside of the parentheses. So we get an a times x squared plus b over ax, adding b squared over 4a squared. When we distribute a times negative b squared times 4a squared, a times b negative. Now we can simplify a little bit. A goes into a squared, and we end up with 4a here. So eventually, when we simplify, we end up with a negative b squared over 4a, adding c. Okay. Now inside the parentheses, the perfect square, and then this is the term we are using. So it's a times x plus b over 2a squared, and minus b squared over 4a adding c. Okay. Eventually, if you switch these two terms, last two terms, you end up with that. And we have we complete the square to turn into a standard form. And from there, we will know that we'll be able to find out the axial symmetry vertex. And the vertex is usually the minimum and the maximum values. Okay. So the vertex of the graph is going to be this. So the way how we get this is by setting x plus b over 2a equal to 0. We get an axial symmetry. So we end up with minus b over 2a from both sides of the equation, x equal to negative b over 2a. And that's x coordinate for the vertex, and the y coordinate should be f of that, negative b over 2a, and f of negative b over 2a. Okay, and that's theoretical perspective of looking at a vertex. In this case, we generalize to any quadratic functions. So as vertex, doing that, and then the y value negative b over 2a, and putting the x coordinate into the function, and we get that. Actually, the y value should be c minus b squared equal to 4a over 4a. So this is f negative b over 2a equal to c minus b squared over 4a. Yeah. The same, but we don't need to memorize all those variable terms. That's why we just use a function notation to make it simpler. So when a is greater than 0, that means it opens upward. Then the vertex, the minimum occurs at x equal to negative b over 2a. The minimum value is f of that, f of negative b over 2a. a is less than 0, that means it opens downward and has a maximum at x equal to negative b over 2a. Maximum value occurs at the f of negative b over 2a. Okay, so that's how we find minimum maximum, just using the a, b, and c. So the path of baseball after being hit is given by a function f of x equal to negative 0.0032x squared plus x plus 3, where f of x is the height of the baseball in feet, and x is the horizontal distance from the home plate, feet. And what's the maximum height of the baseball? So that means since leading coefficient a here, a is equal to negative 0.0032 less than 0, that means parabola opens downward. Then we have that vertex equal to maximum. That's why they're looking for the maximum height, not the minimum height, and that's how we determine what we are looking for. So a is given, b we know that it's 1, coefficient by default is 1 in front of x, c is equal to 3. Okay, and if you just apply the formula, so x of symmetry should be x equal to negative b over 2a. Okay, so we have negative 1 over 2 times negative 0.0032, and let's use the calculator to do that. So let's see what this is. 1 over 2 times 0.0032. The result is positive, so it turned out to be 156.25. We know this must be feet, right? Ft. If you look at the unit, and if you want to get the maximum height here, maximum value, it's equal to f of 156.25. Okay, so now we go back to the function and replace x with 156.25 and put into the calculator, get the result 156.25 square, adding 156.25 and adding 3. Let's see what that is. And then we come up with the maximum height. 0.032 times 156.25. So that, adding 156.25, adding 3. It turned out to be 81.125 feet. Okay, so the maximum height should be 81.125 feet for this baseball to travel. And that's pretty much it.